Picture a universe where nothing has weight, where you could lift a mountain with a single finger, where skyscrapers drift like clouds, and even the tiniest speck of dust floats effortlessly in the air. It sounds like science fiction, but this weightless world is exactly what our reality would resemble without one extraordinary, invisible force, the Higgs Field. This hidden fabric of the cosmos is what gives everything from the stars above to the device in your hand its mass. Without it, the universe as we know it wouldn't just feel different, it wouldn't exist at all. Now here's the mind-bending part. This field isn't some distant cosmic phenomenon. It's everywhere right now, filling the space around you like an unseen ocean. Even as you watch this, particles are moving through it, gaining mass the way a swimmer trudges through water. And the wildest thing, this isn't just abstract physics. The Higgs field is the reason you don't float off the planet, why your coffee stays in the cup, and why the very atoms in your body hold together. It's the invisible architect of our tangible world, and yet, until just over a decade ago, we had no direct proof it was real at all. So why does this matter for the future? Because unlocking the secrets of the Higgs field isn't just about understanding the universe, it's about reshaping it. Imagine technologies that manipulate mass itself, from ultra-light materials that defy gravity to energy breakthroughs that rewrite the rules of physics. This is the frontier where science fiction starts to edge toward science fact. And in this video, we're diving deep into how this elusive force shapes everything from the tiniest particles to the vast expanse of space, and how it might just hold the key to the next leap in human innovation. Stick around, because what you're about to discover will change how you see the world literally. To grasp why the Higgs field is such a game changer, we need to rewind to the building blocks of reality itself. Think of the universe as an incredibly intricate Lego set, except instead of plastic bricks, everything is made of tiny, invisible particles. At the smallest scales, atoms, those familiar building blocks of matter, aren't the end of the story. They're made up of even smaller pieces, protons and neutrons clustered in the nucleus, with electrons whizzing around them like hyperactive fireflies. But if you could peer deeper, you'd find that protons and neutrons aren't fundamental either. They're made of quarks particles so small they've never been split apart, bound together by gluons, the sticky glue of the subatomic world. This is where the Standard Model comes in, our best blueprint for how particles and forces interact. Picture it as the ultimate cosmic rulebook, outlining all known players in the particle zoo and how they behave. There are matter particles like quarks and electrons, force carriers like photons which bring us light and gluons, and even ghostly neutrinos that barely interact with anything at all. But here's the catch. While the Standard Model explains an astonishing amount about the universe, it had one glaring hole for decades. None of these particles should have mass. Yet clearly they do. You don't float into space when you step outside, and mountains don't drift like balloons. Something had to explain why particles, and by extension, everything in the universe, aren't weightless. That missing piece was the Higgs field. Imagine it as an invisible syrup filling all of space. When particles move through it, some barely notice, slipping through like a knife through water. Those are the lightweight particles, like photons. Others, like quarks, trudge through as if wading through molasses, and that resistance is what we experience as mass. Without this field, particles would zip around at the speed of light, never coming together to form atoms, let alone planets or people. It's the reason the universe has substance instead of being a chaotic soup of weightless particles. But here's the twist: the Higgs field isn't just a passive backdrop. It's a dynamic player in the cosmic drama, interacting with particles in ways that shape the very fabric of reality. And understanding it didn't come easy. It took decades of theory, experimentation, and one of the most ambitious scientific instruments ever built to finally catch a glimpse of its fingerprint. That discovery didn't just fill in a gap in the Standard Model. It opened the door to questions we're still trying to answer today. like why do particles have the masses they do? Could there be more hidden fields waiting to be found? And what happens if we learn to tweak this field ourselves? The answers could rewrite the future of technology and our place in the universe. For centuries, scientists grappled with what seemed like a simple question: why does anything have weight at all? The ancient Greeks thought everything was made of earth, air, fire, and water, but even they wondered why some things felt heavier than others. Fast forward to Newton's era, and mass was treated as a fixed property of matter, like an invisible tag attached to every object. But this was just a description, not an explanation. The real mystery lay deeper. Why do fundamental particles, the smallest bits of the universe, resist motion? Why don't they all just zip around at the speed of light? By the early 20th century, Einstein's theory of relativity showed that mass and energy were two sides of the same coin, yet it still didn't answer where mass itself came from. Quantum mechanics revealed a world of particles behaving in bizarre, unpredictable ways, but even there, the equations suggested most particles should be massless. That created a paradox. If the math said particles shouldn't weigh anything, why does the universe clearly have weight? For decades, this gap haunted physicists. They knew something crucial was missing, but what? Enter Peter Higgs and a handful of other theorists in the 1960s, who proposed a radical solution. Perhaps particles gain mass by interacting with an invisible field permeating all of space. At first, the idea seemed almost too strange to take seriously. A field giving mass to things. It sounded like filling the universe with cosmic glue. But the math worked. Just as light slows down when passing through water, particles would slow down in this field, and that resistance would manifest as mass. The heavier the particle, the stronger its interaction with the field. It was an elegant answer to one of physics' biggest puzzles, yet for years it remained just a theory. Skeptics argued that if this field existed, where was the proof? Detecting something invisible and omnipresent seemed impossible. That's when the hunt began for the Higgs boson, a ripple in the field that would confirm its existence. It took colossal machines like the Large Hadron Collider, decades of work, and billions of collisions to finally spot it in 2012. The discovery wasn't just a triumph of science, it validated a whole new way of understanding reality. Suddenly, the universe made sense in a way it hadn't before. Mass wasn't just a property handed out arbitrarily. It was the result of an intricate cosmic dance between particles and a hidden field woven into the fabric of space itself. Yet even now, the Higgs field leaves us with tantalizing questions. Why do particles have the specific masses they do? Could there be other fields like it, still waiting to be discovered? And if we ever learn to manipulate this field, what unimaginable technologies might become possible? The story of mass, it turns out, is far from over. In the quiet halls of Edinburgh University in the early 1960s, a soft-spoken physicist named Peter Higgs scribbled equations that would upend our understanding of reality. He wasn't seeking fame or even expecting to solve one of science's greatest mysteries. He was simply trying to patch a hole in the math. At the time, physicists were wrestling with a glaring inconsistency. Their elegant equations predicted massless particles, yet the universe was clearly full of things with weight. Higgs wasn't alone in pondering this. Across the globe, other brilliant minds, Francois Englert, Robert Brout, Gerald Guralnick, Carl Hagen, and Tom Kibble, were independently circling the same radical idea. What if mass wasn't an intrinsic property but something acquired? The spark came from an unlikely place: superconductivity, the phenomenon where certain materials lose all electrical resistance at extremely low temperatures. In superconductors, particles move without friction, almost as if gliding through an invisible force field. Higgs wondered, could the entire universe be like that? Not with electrons sliding effortlessly, but with particles trudging through a cosmic molasses, a field that clung to them, giving them mass. He drafted a short paper suggesting this very mechanism in 1964. But when he submitted it to a prominent physics journal, the editors rejected it outright. They deemed the idea of no obvious relevance to physics. Undeterred, Higgs revised the paper, this time adding a critical prediction. If his field existed, it should produce a telltale particle, later dubbed the Higgs boson. That addition turned a fringe idea into a testable theory. Meanwhile, half a continent away, Inglet and Brout reached similar conclusions, publishing just weeks before Higgs' revised paper. Then came Guralnik, Hagen, and Kibble, completing a tapestry of independent discoveries. Yet for years, these ideas languished in obscurity. The physics community was skeptical partly because the math was abstract, but also because the proposal sounded almost mystical. A field giving mass to everything, it felt like inventing an invisible ether all over again. Even Nobel laureate Richard Feynman initially dismissed it, scribbling "whack" in the margins of one paper. The tide began to turn when Steven Weinberg and Abdus Salam incorporated Higgs Mechanism into their groundbreaking work, unifying two fundamental forces, electromagnetism and the weak nuclear force. Suddenly, the Higgs field wasn't just an explanation for mass, it was the linchpin holding together the Standard Model itself. Yet without experimental proof, it remained a beautiful but unverified hypothesis. Higgs himself admitted he never expected to see confirmation in his lifetime. It would take the world's largest machine, thousands of scientists, and nearly 5 decades to find that elusive boson, but that's a story for another moment. What's striking about this chapter in science isn't just the brilliance of the idea, but its humility. Higgs wasn't a charismatic self-promoter, he was a reserved theorist who followed the math where it led. His name became attached to the field almost by accident, a quirk of academic citations, and those simultaneous discoveries. They remind us that great ideas often emerge when the time is ripe, bubbling up in multiple minds at once. The Higgs field wasn't invented, it was uncovered, a hidden law of nature waiting patiently for humanity to stumble upon it. And in that stumble lay a profound lesson. Sometimes the universe's deepest secrets are hidden not in distant galaxies, but in the quiet persistence of curious minds. Think of the Higgs field as the universe's ultimate backstage crew, never seen but utterly essential for the show to go on. Unlike gravity or magnetism, which push and pull, this field doesn't exert force in the traditional sense. Instead, it's more like an invisible, ever-present syrup filling every corner of space. When particles travel through it, some glide effortlessly, barely noticing its presence, while others slog through as if fighting against thick molasses. That resistance, the sticky interaction between particles and the field, is what we experience as mass. Take the humble electron, for example. It's like a nimble dancer slipping through the syrup with minimal drag, which is why it's so lightweight. Now compare that to a top quark, the heaviest known fundamental particle. It's the equivalent of wading through wet concrete, clinging to the field with such intensity that it ends up nearly 200,000 times heavier than the electron. Yet both particles are moving through the same cosmic medium. The difference lies in how strongly they interact with it. But here's where it gets even stranger. Some particles, like photons, the particles of light, don't interact with the Higgs field at all. They zip through the universe at full speed, completely unaffected, which is why light has no mass. If every particle behaved this way, the universe would be a chaotic, weightless frenzy. No atoms, no planets, no you. The Higgs field is the reason reality has structure instead of chaos. Now imagine dipping different objects into honey. A feather would barely pick up any coating, while a marble would emerge thickly draped. That's essentially how the Higgs field behaves. It doesn't give mass to particles. It's more accurate to say particles acquire mass by how they engage with the field. The more they stick, the heavier they become. This subtle distinction is why the Higgs mechanism isn't just about explaining mass, it's about revealing a hidden layer of cosmic choreography, one that dictates how the universe's building blocks fit together. And here's the kicker: without this field, the laws of physics as we know them would collapse. The delicate balance enabling atoms to form, stars to ignite, and life to emerge hinges on this invisible interaction. It's not just a scientific curiosity, it's the silent architect of everything tangible. So the next time you feel the weight of your phone in your hand or the pull of gravity keeping you grounded, remember, you're not just holding an object or standing on Earth. You're sensing the Higgs field at work, the unseen hand shaping the very fabric of your reality. The key to understanding the Higgs mechanism lies in a simple but profound shift in perspective. Mass isn't something particles inherently possess. It's something they acquire by moving through the universe's hidden molasses. Picture a bustling cocktail party where guests represent particles and the room itself is the Higgs field. When an unknown guest, say an electron, enters, they might slip through unnoticed, exchanging only brief nods with a few people. That minimal interaction mirrors how lightweight particles glide through the Higgs field, picking up just a tiny bit of mass. But now imagine a celebrity walking in. The crowd immediately swarms them, slowing their progress as they're bombarded with handshakes and selfie requests. That's the equivalent of a top quark, a particle that interacts so intensely with the field that it gains enormous mass, as if trudging through an ocean of admirers. This metaphor reveals a crucial nuance. The Higgs field doesn't hand out mass like a cosmic vending machine. Instead, particles gain mass based on how strongly they socialize with it. Electrons and quarks, for instance, interact through a fundamental force called the Yukawa coupling. Think of it as their unique handshake style with the field. The tighter the grip, the more mass they accumulate. Photons, on the other hand, are like partygoers who refuse to engage. They zip through untouched, which is why light remains massless. But here's where the mechanism gets even more elegant. The Higgs field isn't just passive syrup or a static party venue. It's a dynamic entity with its own energy state. In the early universe, right after the Big Bang, this field was like a marble balanced precariously atop a hill, teetering at a high energy state where particles couldn't gain mass. Then, as the cosmos cooled, the field rolled down into a stable valley, settling into its current energy minimum. That shift is what physicists call symmetry breaking. The moment the universe's rules changed, allowing the Higgs mechanism to kick in. Suddenly, particles could interact with the field differently, and mass emerged as a new feature of reality. To see why this matters, imagine flipping the scenario. If the Higgs field had settled into a different energy state, or never broken symmetry at all, quarks might have zipped around like photons, unable to form protons or neutrons. Atoms wouldn't exist, stars wouldn't ignite, life as we know it would be impossible. The Higgs mechanism isn't just a quirk of particle physics, it's the reason the universe has structure instead of chaos. Now let's zoom into the subatomic realm for a concrete example. When an electron moves through the Higgs field, it's like a kayak paddling through calm water. It encounters just enough resistance to give it a tiny bit of heft. But a quark, that's a cargo ship plowing through heavy waves, its mass bloated by relentless interactions with the field, and the Higgs boson itself. The particle discovered in 2012 is like a splash from that cargo ship, a ripple in the field that confirms the syrup's existence. Each of these interactions is governed by the same underlying principle. Mass isn't handed down from on high. It's earned through a relentless, invisible dance between particles and the fabric of space itself. What's truly humbling is realizing this dance isn't confined to distant stars or particle colliders. It's happening right now in the device you're holding, in the air you're breathing, even in the neurons firing in your brain as you process these words. The Higgs mechanism isn't an abstract theory, it's the silent choreographer of your everyday reality. And while we've uncovered its basic steps, the full routine, why particles have the masses they do, whether other fields lurk in the cosmic background, remains one of physics' greatest unfinished performances. Finding the Higgs boson was like detecting a whisper in a hurricane, a fleeting, elusive signal buried in an avalanche of particle collisions. This tiny ripple in the Higgs field doesn't just prove the field exists. It's the smoking gun that convinced the scientific community the entire mechanism wasn't just theoretical fantasy. Imagine trying to confirm the existence of an ocean by catching a single droplet mid-splash. That's the scale of the challenge physicists faced when hunting for this particle. Unlike protons or electrons, which are stable enough to study directly, the Higgs boson is absurdly short-lived. It decays into other particles within a septillionth of a second. You can't trap it in a bottle or observe it under a microscope. Instead, scientists had to recreate the fiery conditions of the early universe, smashing protons together at nearly the speed of light in the 27-kilometer ring of the Large Hadron Collider. These collisions briefly concentrate enough energy to excite the Higgs field, like tossing a pebble into a pond and watching the momentary bulge of water where it lands. The boson is that fleeting ripple, a disturbance in the field's otherwise smooth surface. But here's where it gets even trickier. The boson doesn't announce itself with a fanfare. It leaves behind only cryptic debris-specific patterns of lighter particles that hint at its brief existence. Detecting it required sifting through billions of collisions, searching for statistical anomalies that matched theoretical predictions. When researchers finally spotted those telltale patterns in 2012, it wasn't just a eureka moment, it was a validation of decades of painstaking work. The boson's discovery didn't just fill in a blank in the standard model. It confirmed that the universe truly operates on this invisible, molasses-like scaffolding. What's fascinating is how much this particle reveals about the field itself. The boson's mass, about 125 times heavier than a proton, tells us how sticky the Higgs field is. A lighter boson would imply a weaker field, barely giving particles any mass. A heavier one would suggest a field so clingy that atoms might never have formed. The fact that it landed precisely where theory predicted is a testament to the elegant symmetry of nature's design. Yet the discovery raised as many questions as it answered. Why does the Higgs boson have this exact mass and not some other value? Could there be multiple types of Higgs particles, like echoes of the field we haven't detected yet? And most tantalizingly, if we can measure the boson's properties with even greater precision, might they reveal cracks in the standard model, pointing toward undiscovered physics? The Higgs boson isn't just a trophy from one of science's greatest hunts. It's a key to unlocking deeper layers of cosmic mystery. So the next time you hear about the God particle, a nickname most physicists loathe, by the way, remember, it's not some divine relic. It's the fingerprint of an invisible force that makes your everyday reality possible. Without it, the universe would be a featureless void, devoid of stars, planets, or even the device you're using right now. The Higgs boson is proof that sometimes the most profound truths come disguised as the faintest whispers in the data. Buried 100 meters beneath the border of France and Switzerland lies a 27-kilometer ring of superconducting magnets colder than outer space, capable of hurling protons at 99.9999991% the speed of light. This isn't science fiction, it's the Large Hadron Collider, humanity's most ambitious microscope, built to peer into realms smaller than atoms and hotter than stars. Picture a steel racetrack where particles complete 11,000 laps every second, colliding head-on with energies unseen since the universe's first trillionth of a second. The LHC isn't just a machine, it's a time machine recreating conditions so primal they haven't existed for 13.8 billion years. Every component pushes engineering to its limits. The magnets guiding those protons, they're cooled to -271 degrees Celsius by liquid helium, making them among the coldest spots in the known universe. The vacuum inside the beam pipes 10 times emptier than deep space, ensuring not a single gas molecule disrupts the proton's path. And when those particles collide, they pack the energy of a freight train into a space 1,000,000 times smaller than a grain of sand. Managing these extremes requires tech that didn't exist when the project began, like supercomputers processing a petabyte of data every second, equivalent to streaming 200,000 HD movies simultaneously. But why build such a colossus? Because nature hides its secrets well. The Higgs boson doesn't appear in everyday conditions. You need to agitate the Higgs field violently enough to make it splash. Think of trying to detect waves in a pond by dropping pebbles. If your pebble's too small, the ripples vanish before you see them. The LHC isn't dropping pebbles, it's hurling boulders, creating collisions so energetic they momentarily warp spacetime itself. What makes the LHC extraordinary isn't just its scale, but its precision. Detectors like ATLAS and CMS, each weighing more than the Eiffel Tower, act as ultra-high-speed cameras, capturing snapshots of collisions in billion-pixel detail. They don't see the Higgs boson directly. They track its decay products, like reconstructing a dinosaur from fossilized footprints. Every second, 600 million particle interactions occur in these detectors, but only a handful might hint at the Higgs. Filtering that signal from the noise is like finding a single unique snowflake in a blizzard. The collider's true genius lies in its duality. It's both a sledgehammer and a scalpel, brute enough to crack open the universe's deepest layers, yet delicate enough to measure quantum whispers. And its impact stretches far beyond Higgs hunting. From simulating quark-gluon plasma, a state of matter last seen microseconds after the Big Bang, to probing extra dimensions predicted by string theory, the LHC is rewriting textbooks one collision at a time. Yet for all its complexity, its purpose is elegantly simple: to uncover the rules written into the fabric of reality itself. Here's the mind-blowing part: we've barely scratched the surface. With upgrades already underway to boost its power tenfold, the LHC's greatest discoveries may still lie ahead. Who knows what secrets will emerge when we push this machine and our understanding to the edge of the impossible. On July 4, 2012, a hushed tension filled the auditorium at CERN as scientists from the ATLAS and CMS collaborations prepared to make an announcement decades in the making. The air was electric, not just in that room, but across the global physics community. Live streams connected researchers from Tokyo to Chicago, all leaning into their screens as if trying to catch every syllable. Then came the moment, a telltale bump in the data, a statistical anomaly at 125 gigaelectronvolts, the unmistakable signature of the Higgs boson. The room erupted, not with the dramatic flair of a Hollywood discovery scene, but with something far more profound: quiet gasps, murmured exclamations in a dozen languages, and the weighty realization that humanity had just brushed against one of nature's best-kept secrets. This wasn't just another particle discovery. It was the capstone of a 50-year quest, the final piece of the Standard Models puzzle. Newspapers worldwide splashed the news with headlines usually reserved for moon landings or royal weddings. Why? Because this tiny, fleeting particle confirmed something extraordinary: that the universe is pervaded by an invisible field giving everything its substance. Peter Higgs, then 83 years old and present in the audience, wiped away tears as the data flashed on screen. The boson bearing his name, a concept once mocked as widget physics, was now as real as the chair he sat on. Behind that euphoria lay an almost unimaginable effort. The LHC had generated over 500 quadrillion proton collisions by then, a staggering number equivalent to every grain of sand on Earth's beaches multiplied by 50. Hidden in that avalanche of data were perhaps a few thousand Higgs events, each lasting less time than it takes light to cross a single atom. Isolating those events required algorithms so precise they could spot a single misspelled word across every book in the Library of Congress twice over. The announcement carried a peculiar humility. Scientists carefully avoided claiming they'd found the Higgs boson outright. Instead, they spoke of a 5 sigma signal, statistical jargon meaning there was only a 1 in 3.5 million chance the bump was a fluke. That cautious phrasing captured science at its best, triumphant yet disciplined, celebratory yet rigorous. And when independent teams from Atlas and CMS presented identical results within minutes of each other, it wasn't just confirmation, it was poetry in peer review. Beyond the physics world, the discovery rippled through culture. Late-night hosts cracked jokes about the God particle, while theologians debated whether science had erased divine mystery or deepened it. Economists calculated the return on investment, billions spent to answer an abstract question, and found it sparked advances in computing, medicine, and material science that likely paid for the collider many times over. But perhaps the most poignant impact was on young minds. Enrollment in physics programs surged globally as a new generation saw that the universe's grandest questions weren't just solvable, they were worth solving. Yet for all its fanfare, the 2012 announcement wasn't an ending. It was a doorway, confirming the Higgs boson meant we'd finally mapped the known universe's rulebook, but standing at that threshold, we glimpsed how much lay beyond. The boson's mass hinted at mysteries the standard model couldn't explain, from dark matter's identity to the universe's precarious stability. In that sense, the discovery was less a finale and more a cosmic invitation, one we're still learning how to accept. Confirming the existence of the Higgs boson wasn't as simple as spotting a blip on a screen. It required an orchestrated symphony of particle collisions, algorithmic precision, and painstaking verification. Picture a needle buried in a haystack the size of Mount Everest, except the needle vanishes within a nanosecond, and the haystack is constantly exploding. That's the scale of the challenge scientists faced. The process began with the Large Hadron Collider smashing protons together with unimaginable force, generating showers of particles. But the Higgs boson itself never appears directly in the debris. Instead, it decays almost instantly into lighter, more stable particles like photons or electrons. Detecting it meant reconstructing these decay patterns like forensic scientists piecing together a crime scene from scattered clues. The key lay in statistical significance. Physicists don't declare discoveries based on a handful of events. They need overwhelming evidence. For the Higgs, that meant identifying a consistent excess of specific decay products at an energy of around 125 gigaelectronvolts. Think of it as tuning a radio to a noisy frequency. You're listening for a faint melody buried in static. At first, the signal was just a whisper in the data. But as the LHC accumulated more collisions, that whisper grew into a chorus. By the summer of 2012, the Atlas and CMS collaborations had each independently spotted the same telltale bump in their datasets. The chance this was a random fluctuation, less than 1 in 3.5 million. Peer review added another layer of rigor. Before the announcement, hundreds of scientists scrutinized every step, from how detectors were calibrated to whether background noise could mimic the signal. Rival teams even cross-checked each other's work, a process as tense as it was collaborative. When both experiments presented matching results with 5 sigma certainty, the gold standard in particle physics, the community finally exhaled. This wasn't just one team's triumph, it was a validation of the scientific method itself. The real magic happened in the aftermath. Discovering the boson wasn't the end, it was a starting point. Measuring its properties with ever greater precision became the new frontier. Does it decay exactly as predicted? Could slight deviations hint at undiscovered physics? Every new measurement is like adjusting a microscope's focus, revealing finer details of the Higgs field's role in shaping reality. And with upgrades pushing the LHC to even higher energies, who knows what other secrets might emerge from the data? The story of the Higgs boson isn't just about confirming a theory, it's about learning how to ask better questions of the universe. The Higgs field isn't just a scientific curiosity, it's the silent architect of reality as we know it. Without this invisible force, the universe would be an entirely different place, devoid of stars, planets, or even the atoms that make up your body. Think about that for a moment. Every tangible thing you interact with, your coffee cup, the chair you're sitting on, even the air you breathe, owes its very existence to this elusive field. But the implications run far deeper than just giving mass to particles. The Higgs field shapes the fundamental laws of physics, determining how matter interacts, how forces behave, and ultimately, how the cosmos evolved from a searing hot plasma into the structured universe we see today. Consider the early moments after the Big Bang, when the universe was a chaotic soup of massless particles zipping around at the speed of light. As the cosmos cooled, the Higgs field underwent a dramatic phase transition, shifting from a high-energy state to its current stable form. That shift wasn't just a minor adjustment, it was the moment the universe gained structure. Particles that had been weightless suddenly began interacting with the field, slowing down and clumping together, forming the first protons, neutrons, and atoms. This process didn't just create matter. It dictated the rules for how galaxies, stars, and planets would eventually form. Without that critical transition, reality would have remained a formless, featureless void. But here's where it gets even more profound. The Higgs field doesn't just explain why particles have mass, it helps answer one of the biggest questions in physics: why does anything exist at all? The field's energy state is finely tuned in a way that allows atoms to be stable. If its properties were even slightly different, if the field were stronger or weaker by a hair, protons might decay instantly, electrons could lose their grip on atomic nuclei, and complex structures like molecules or living cells would never have a chance to form. The fact that we're here pondering these questions is a direct consequence of the Higgs field's precise calibration. This leads to another jaw-dropping realization. The Higgs field might hold the key to understanding the ultimate fate of the universe. Recent measurements suggest that the field's current state is metastable, like a ball resting in a shallow valley, poised to roll into a deeper one. If the field were to suddenly shift to a lower energy state, it could trigger a catastrophic phase transition, rewriting the laws of physics in an instant. Stars, planets, and even atoms would cease to function as they do now. While this scenario isn't likely to happen anytime soon, if ever, it underscores how the Higgs field isn't just a passive backdrop but an active player in the cosmic drama. Yet for all its importance, the Higgs field also highlights how much we still don't understand. Its discovery confirmed a major piece of the Standard Model, but it also exposed gaps in our knowledge. Why, for instance, does the Higgs boson have the mass it does? The math suggests it should be much heavier, unless there's something else at play, some undiscovered physics balancing the scales. Some theories propose hidden particles or even parallel Higgs fields lurking in the quantum shadows. Others wonder if the field's properties could hint at a deeper connection to dark matter, the mysterious substance making up most of the universe's mass. What's clear is this: the Higgs field isn't just a footnote in physics textbooks. It's the invisible scaffold holding reality together, shaping everything from the tiniest particles to the grandest cosmic structures. And as we continue probing its secrets, we're not just learning about how the universe works, we're uncovering the very conditions that made life possible in the first place. That's the true power of this discovery. It's not just about filling in a gap in our knowledge, it's about rewriting our place in the story of existence itself. To grasp how the Higgs field shaped the early universe, we need to rewind to the very first moments after the Big Bang, a time when reality was so blisteringly hot and dense that the fundamental forces we know today were still fused into one. In those initial fractions of a second, temperatures exceeded a quadrillion degrees and particles raced around at light speed, utterly weightless. The Higgs field existed even then, but it was in a vastly different state, like a spring coiled under immense pressure, waiting to snap into place. During this primordial chaos, the universe was symmetrical in a way that's almost impossible to imagine today. The four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces were indistinguishable, blended into a single superforce. Particles like quarks and electrons behaved identically, oblivious to concepts like mass or inertia. But as the cosmos expanded and cooled, something extraordinary happened. Around a trillionth of a second after the Big Bang, the temperature dropped enough for the Higgs field to undergo a cosmic phase transition, like water freezing into ice. This shift wasn't just a minor adjustment, it was a revolution. The field settled into its current state, breaking the universe's perfect symmetry. Suddenly, particles that had been racing around unimpeded began interacting with the field, slowing down as if moving through thickening syrup. Quarks, once weightless, gained heft, allowing them to clump together into protons and neutrons. Electrons acquired just enough mass to orbit atomic nuclei without instantly escaping. Even the weak nuclear force responsible for radioactive decay split off from electromagnetism, a divorce made possible because the Higgs field gave its force-carrying particles mass. The consequences of this transition were cosmic in every sense. Without it, quarks would have remained free, unable to bind into atoms. The universe would have been an eternal soup of weightless particles, forever expanding without structure. No stars, no planets, no chemistry, just a thin, homogeneous haze. But thanks to the Higgs field, matter gained the ability to cluster, collapse, and ignite under gravity's pull. The first atoms formed, gas clouds coalesced, stars flared to life, forging heavier elements in their cores. In essence, the Higgs field didn't just give particles mass, it gave the universe texture, allowing complexity to emerge from chaos. Yet the field's influence didn't stop there. Its precise energy state acted like a cosmic dial, fine-tuning the universe's expansion rate. If the Higgs field had been even slightly stronger, particles might have become too heavy, causing matter to collapse back on itself before galaxies could form. Too weak, and particles would have remained nearly massless, preventing gravity from ever gathering them together. It's a staggering realization. The Higgs field didn't just enable matter to exist, it determined whether the universe could host anything as intricate as life itself. What's even more remarkable is that we're seeing echoes of this phase transition today. The Large Hadron Collider recreates these primordial conditions in miniature, smashing particles together at energies that temporarily melt the Higgs field back into its early, symmetrical state. In those fleeting moments, detectors catch glimpses of a universe without mass, a window into what reality could have been, had the Higgs field never snapped into place. This raises a tantalizing question. Was this transition inevitable, or was there an element of chance? Some theories suggest our universe might be one of many, each with a Higgs field settling into different states, most of them sterile, incapable of supporting complexity. If true, it means our existence hinges on a cosmic lottery ticket, a 1 in a trillion alignment that allowed matter to gain just the right amount of heft. The Higgs field isn't just a relic of the Big Bang, it's the silent architect of our cosmic luck, the reason we're here to ponder it at all. While the Higgs field gives mass to particles like electrons and quarks, not everything in the universe plays by those rules. Meet the rebels of the particle world, photons and gluons, the only known fundamental particles that zip through the cosmos completely untouched by the Higgs field. Imagine them as cosmic ninjas, slipping past the field's sticky influence without leaving a trace. This isn't just a quirky exception, it's a clue to how the universe balances its forces with exquisite precision. Take the photon, for example, the particle of light. When you flip a light switch, photons race to your eyes at the universe's ultimate speed limit, 299,792,458 meters per second. No hesitation, no slowdown. Why? Because photons don't interact with the Higgs field at all. They're like a perfectly lubricated skate gliding across an infinite rink, encountering zero friction. This isn't an accident, it's baked into the laws of electromagnetism. If photons had mass, light would behave drastically differently. stars would twinkle less, lasers wouldn't work as precisely, and even your Wi-Fi signal would struggle to penetrate walls. The Higgs field's indifference to photons isn't a bug. It's a feature critical to how energy moves through the universe. Then there are gluons, the unsung heroes holding atomic nuclei together. These particles carry the strong nuclear force, acting like microscopic bungee cords between quarks. Despite their sticky job, gluons themselves are weightless, darting between quarks without ever getting bogged down by the Higgs field. If they did have mass, atoms would fly apart instantly. Protons and neutrons couldn't form, and the universe would be a soup of loose quarks. The fact that gluons remain massless is what allows them to transmit their force over such incredibly short distances, keeping your atoms, and by extension, you intact. So why do some particles escape the Higgs field's grip while others can't break free? The answer lies in symmetry, a kind of cosmic balancing act embedded in the laws of physics. Photons and gluons belong to a special class called gauge bosons, particles that mediate fundamental forces. For these particles to do their jobs correctly, certain symmetries in nature's equations require them to be massless. It's not that the Higgs field ignores them, it's that their very existence depends on resisting its influence. Break that symmetry, and suddenly forces like electromagnetism or the strong nuclear force would behave unpredictably, destabilizing everything from chemical reactions to stellar fusion. This duality, massive particles giving the universe structure, massless particles enabling its forces, creates a delicate equilibrium. Without massless photons, energy couldn't travel vast distances across space. Without massless gluons, matter itself would disintegrate. Yet without the Higgs field's influence on other particles, there'd be no stable matter for light to illuminate or forces to bind. Together, they form a cosmic partnership where each player's role is non-negotiable. What's truly astonishing is how this balance emerges from seemingly arbitrary rules. The Higgs field doesn't decide which particles get mass. Their interactions are determined by deeper principles woven into the fabric of reality. That's why studying massless particles isn't just about cataloging exceptions, it's about probing the boundaries of why our universe operates the way it does. And as we'll see next, this fine-tuned dance between mass and masslessness might hold even deeper secrets about forces we've yet to discover. But there's a cosmic puzzle lurking beneath the Higgs field's triumph, one that keeps physicists awake at night. If the math behind particle physics is correct, the Higgs boson should be unimaginably heavy, potentially as massive as the Planck scale, a number so large it dwarfs the entire observable universe. Yet when scientists finally measured it, the boson weighed in at a mere 125 gigaelectronvolts, light as a feather compared to those sky-high predictions. This glaring mismatch between expectation and reality is called the hierarchy problem, and it's one of the most nagging mysteries in modern physics. To grasp why this discrepancy matters, imagine building a house where the foundation is balanced precariously on a single playing card. The structure above might be perfectly stable, but you'd instinctively ask, how is that card supporting so much weight without collapsing? The Higgs boson's mass is that playing card. According to quantum theory, the boson's mass should be pushed up to extreme values by interactions with other particles, especially heavy ones we haven't even discovered yet. Think of it like a celebrity constantly bombarded by paparazzi. Their presence alone should inflate the Higgs mass to absurd levels, but somehow, against all odds, it remains shockingly lightweight. This isn't just a trivial accounting error. The hierarchy problem hints that our understanding of the universe might be missing a critical piece. One leading explanation involves supersymmetry, a theory proposing every known particle has a heavier superpartner. These shadowy twins could theoretically cancel out the quantum corrections pushing the Higgs mass upward, like two opposing teams in a tug of war ending in a perfect standstill. The catch, despite decades of searching, not a single superpartner has shown up in particle colliders. Another possibility is that the Higgs boson isn't fundamental at all. It might be a composite particle woven from even smaller threads we can't yet detect. Picture a snowflake from afar. It looks like a single object, but zoom in and you'll see it's made of countless water molecules. If the Higgs works similarly, its unexpectedly low mass could stem from the behavior of its hidden constituents. Then there's the multiverse angle. Some theorists suggest our universe just happens to exist in a rare bubble where the Higgs mass is improbably fine-tuned for life. In this scenario, most universes have Higgs particles so heavy that atoms never form. We just lucked out living in the one where the numbers lined up perfectly. It's a controversial idea, but it underscores how deeply the hierarchy problem challenges our search for cosmic order. What makes this puzzle so urgent is its connection to the universe's fragility. The Higgs mass doesn't just defy expectations, it sits perilously close to a threshold that could make reality unstable. A slightly heavier boson might have caused the cosmos to collapse in on itself moments after the Big Bang. A lighter one could have left particles too weightless to clump into galaxies. The fact that we're here to ponder this suggests the Higgs mass isn't random, it's a delicate balancing act with existential stakes. For now, the hierarchy problem remains wide open, a gaping hole in the standard model's otherwise tidy framework. Solving it might require rewriting our theories entirely, or uncovering particles and forces that redefine reality as we know it. Until then, every new experiment, from upgraded colliders to ultra-sensitive detectors, brings us closer to answering one of physics' most profound questions. Why is the universe built on such a razor's edge? Supersymmetry isn't just a fancy word from theoretical physics, it's a daring idea that could rewrite our understanding of the universe's most delicate balancing act. Remember the hierarchy problem, that glaring mismatch between how heavy the Higgs boson should be and how feather-light it actually is. Supersymmetry, often called SUSY for short, offers an elegant fix. The theory proposes that every known particle in the universe has a hidden, heavier twin, a superpartner lurking just beyond our current detection. These shadow particles wouldn't just be cosmic curiosities. They'd act like invisible counterweights, perfectly cancelling out the quantum effects that ought to inflate the Higgs boson's mass to impossible levels. Think of it like a seesaw with two equally matched kids. No matter how much they bounce, the board stays level. But here's where it gets wild. These superpartners wouldn't just solve the Higgs mass puzzle. They could also explain dark matter, the mysterious substance making up 85% of the universe's mass. The lightest supersymmetric particle, often dubbed the neutralino, wouldn't interact with light or ordinary matter, making it a prime candidate for this cosmic ghost. SUSY doesn't just tidy up the math, it weaves together two of physics' greatest mysteries into a single framework. Yet for all its elegance, supersymmetry has stubbornly refused to show up where we expected. The Large Hadron Collider has scoured energy ranges where these particles should have appeared, only to come up empty-handed. Some theorists argue we might have been looking in the wrong places. Perhaps superpartners are heavier than predicted, or they decay in ways we haven't yet learned to spot. Others suggest SUSY might manifest in subtle tweaks to the Higgs boson's behavior, like slight deviations in how it decays. The latest LHC upgrades are hunting for these fingerprints with unprecedented precision, probing collisions for whispers of supersymmetry's existence. What keeps scientists hooked is the theory's breathtaking symmetry. SUSY doesn't just add particles willy-nilly. It posits a deep mathematical harmony between matter particles like electrons and quarks and force carriers like photons. In a supersymmetric universe, these categories blur, revealing a cosmos far more interconnected than we ever imagined. It's the kind of beautiful symmetry that physicists adore, a clue that nature might prefer elegance over arbitrary rules. But beauty alone isn't proof. The absence of superpartners so far has led some to explore radical alternatives. Maybe the hierarchy problem isn't about missing particles, but about extra dimensions tiny, curled up layers of space where gravity leaks away, diluting its apparent weakness. Or perhaps the Higgs boson's mass is set by cosmic chance, a random roll of the dice in a multiverse where most universes aren't so lucky. These ideas sound like sci-fi, but they're serious attempts to grapple with a universe that refuses to fit our neatest boxes. For now, Sussy remains tantalizingly out of reach, a theory too compelling to abandon but too elusive to confirm. Whether it's waiting in unexplored energy realms or destined to join history's discarded hypotheses, its legacy is already profound. It's pushed colliders to new heights, inspired generations of physicists, and shown us just how much we still don't understand about the invisible forces sculpting reality. The hunt for supersymmetry isn't just about particle physics. It's a test of whether the universe plays by the elegant rules we dream it does, or if it's far stranger than we've dared to imagine. The Higgs field may hold the key to unlocking one of the cosmos' most perplexing riddles: dark matter. This invisible substance outweighs all visible matter in the universe 5-1, yet it refuses to interact with light or ordinary particles, leaving scientists to chase its shadow through gravitational ripples alone. What if the Higgs field, already responsible for giving mass to known particles, also governs the hidden bulk of the universe's matter? One compelling theory suggests dark matter could be made of particles that interact exclusively through the Higgs field. Imagine a stealthy cosmic neighbor living in the same house as you, sharing the same walls, the same floors, yet never crossing paths because they only respond to one thing: the invisible syrup of the Higgs field. These hypothetical particles, dubbed Higgs portal dark matter, would acquire mass just like quarks or electrons but remain otherwise undetectable to our instruments. Experiments like the Large Hadron Collider are hunting for traces of these ghostly interactions, searching for anomalous energy losses in collisions that could signal a Higgs boson decaying into invisible dark matter particles. Another tantalizing possibility ties back to supersymmetry. If superpartners exist, the lightest among them, often called the neutralino, could be stable enough to persist throughout cosmic history, accumulating in vast halos around galaxies. This particle wouldn't just solve the Higgs mass hierarchy problem, it might also be the dark matter we've been seeking. The Higgs field here acts as a bridge, connecting the visible world to this shadow realm through subtle quantum effects. But the most radical idea comes from theorists who propose the Higgs field itself might have a dark counterpart, a twin field that permeates the universe just as pervasively but interacts only with dark matter. Picture two parallel oceans overlapping in space, one familiar and brimming with fish, the other silent and unseen yet equally vast. If true, this could explain why dark matter clusters so differently around galaxies than ordinary matter, as if guided by its own invisible currents. Cutting-edge experiments are pushing these theories to the test. Deep underground, detectors like LUX Zeppelin wait for the rare jostle of a dark matter particle bumping into an atomic nucleus. In space, telescopes like the James Webb analyze how dark matter bends light around distant galaxies, searching for clues about its composition. And at CERN, physicists are scrutinizing Higgs boson decays with nanometer precision, hoping to catch it spitting out something unexpected. What makes these searches so electrifying is their potential to crack two mysteries at once. Unraveling dark matter wouldn't just tell us what most of the universe is made of, it might reveal new layers to the Higgs field itself, showing us how deeply its influence runs. Whether through hidden particles, shadowy superpartners, or an entirely new field, the answer could rewrite our understanding of mass, matter, and the very fabric of reality. And if history is any guide, the universe has a habit of being far stranger and more interconnected than we dare assume. When scientists first set out to detect the Higgs boson, they weren't just probing the origins of mass, they were building tools that would revolutionize fields far beyond particle physics. The technology developed to hunt this elusive particle has spun off into breakthroughs that touch our lives daily, from saving lives in hospitals to turbocharging the computers in our pockets. Take medical imaging, for instance. The same superconducting magnets that steer protons at nearly light speed in the Large Hadron Collider now power MRI machines with unprecedented precision. These devices rely on magnets chilled to temperatures colder than deep space, a technology refined over decades of particle accelerator research. Without the push to detect the Higgs, we might still be waiting for MRI scans sharp enough to spot tumors the size of a grain of rice. But the innovations don't stop there. Detecting Higgs bosons requires processing unfathomable amounts of data. Think sifting through every tweet ever posted in under a second. To tackle this, CERN pioneered distributed computing grids, laying the groundwork for the cloud-based systems that now power everything from streaming services to AI chatbots. The World Wide Web itself was born here, invented as a way for physicists to share data across continents. Today's internet owes its existence to the collaborative spirit of Higgs hunters. Even cancer treatment has benefited. Proton therapy, a cutting-edge radiation technique that zaps tumors with pinpoint accuracy, uses accelerator technology derived directly from particle physics. Unlike conventional radiation, which can damage healthy tissue, proton beams stop precisely at the tumor site, a precision made possible by the same physics that guides particles through the LHC's tunnels. Hospitals worldwide now use these systems, offering hope to patients with once untreatable cancers. Then there's materials science, the ultra-high vacuums inside particle detectors, where even a single stray molecule can ruin an experiment, have inspired new ways to manufacture microchips. Companies leverage these vacuum techniques to create smaller, faster processors, packing more computing power into devices thinner than a credit card. And let's not forget cryogenics, the science of extreme cold. Keeping the LHC's magnets superconducting requires cooling systems so advanced they're now used to preserve biological samples and even prototype quantum computers. Perhaps the most unexpected spin-off lies in renewable energy. Superconducting cables tested for particle accelerators could one day revolutionize power grids, transmitting electricity with zero loss over vast distances. Imagine a future where solar farms in deserts power cities thousands of miles away without wasting a single watt, all thanks to tech honed in the quest for the Higgs. What ties these innovations together is their origin in pure curiosity. No one building the LHC's magnets knew they'd lead to better MRI machines, just as the inventors of the web didn't foresee social media. Yet history shows that probing the universe's deepest mysteries rarely stops at discovery. It ripples outward, transforming our world in ways even the visionaries couldn't predict. The Higgs field may explain why things have mass, but its legacy, that's measured in lives saved, technologies born, and horizons expanded far beyond the lab. Imagine flipping a switch and instantly making objects lighter than air, not by counteracting gravity with some brute force engine, but by dialing down their very essence of mass through the Higgs field. This isn't just science fiction, it's a tantalizing possibility rooted in the same physics that gives particles their weight. Picture a spacecraft where the hull's mass could be adjusted mid-flight, reducing fuel needs to a fraction of current requirements. Or construction materials that become feather-light when transported, then regain their strength upon arrival. The key lies in understanding that mass isn't an immutable property. It's a dynamic relationship between particles and the Higgs field. If we could temporarily weaken that interaction, even slightly, the implications would rewrite entire industries. The most immediate application might be energy production. Today's nuclear reactors rely on splitting heavy atoms like uranium, releasing energy stored in their nuclei. But if we could manipulate the Higgs field to make certain particles artificially heavier or lighter, we might unlock entirely new energy pathways. For instance, making protons temporarily heavier could enhance nuclear fusion. the process powering stars by forcing atomic nuclei to collide more forcefully at lower temperatures. Alternatively, tweaking electron mass could revolutionize superconductors, enabling lossless power grids that operate at room temperature instead of near absolute zero. The Higgs field isn't just a bystander in these scenarios, it's the ultimate control panel for matter's behavior. Then there's propulsion. Anti-gravity might sound like fantasy, but engineers are already exploring concepts like mass shielding, using electromagnetic fields to create localized disturbances in the Higgs field. In theory, this could reduce an object's effective mass without altering its composition, allowing it to defy gravity with minimal energy input. NASA's Advanced Concepts Office has studied similar ideas for interstellar travel, where even a tiny reduction in spacecraft mass could slash journey times by years. Unlike traditional rockets battling Earth's gravity well, a Higgs-modulated vehicle might ascend as effortlessly as a bubble rising through water, but the wildest potential lies in materials science. Imagine programmable matter constructed from metamaterials whose mass properties adjust on demand. A bridge could reinforce itself during earthquakes by increasing the Higgs interaction in its support structures. Emergency shelters might weigh nothing when transported, then stabilize into impenetrable barriers when deployed. Even consumer tech could transform, phones that feel weightless in your pocket yet remain durable, or athletic gear that lightens during motion to enhance performance. Of course, the hurdles are staggering. Manipulating the Higgs field requires energies currently only achievable in particle colliders, and the side effects are unknown. Tinkering with mass could inadvertently alter atomic stability or even spacetime itself. Yet the mere possibility ignites the imagination, reminding us that the universe's deepest secrets often become tomorrow's breakthroughs. Every paradigm-shifting technology from electricity to quantum computing began as an improbable dream. The difference now, we're not just dreaming, we've proven the Higgs field exists. The next step is learning how to converse with it. Quantum fluctuations aren't just background noise in the universe, they're a relentless churn of energy at the smallest scales, constantly reshaping the fabric of reality. Even in what we perceive as empty space, particles blink in and out of existence, borrowing energy from nothingness before vanishing again. This quantum froth doesn't just dance around the Higgs field, it tugs at it, distorting its energy landscape like invisible fingers pressing on a cosmic trampoline. And here's the mind-bending part. These tiny, ephemeral disturbances might hold the answer to one of physics' most urgent questions: is our universe sitting on a knife edge of stability or teetering toward collapse? Picture the Higgs field as a ball resting in a valley, representing its lowest energy state. Quantum fluctuations act like microscopic earthquakes, constantly jostling that ball. Most of the time, these tremors are harmless, the ball wobbles but stays put. But according to quantum theory, there's a terrifying possibility. If fluctuations ever bump the ball over a nearby energy peak, it could roll into an entirely new valley, a lower energy state where the laws of physics as we know them cease to apply. In this scenario, the Higgs field would undergo a catastrophic phase transition, rewriting the rules of reality in an expanding bubble that moves at the speed of light. Stars, planets, and atoms would unravel before anyone could notice, replaced by a new, alien physics we can scarcely imagine. This isn't just theoretical doom-mongering. Precise measurements of the Higgs boson's mass suggest our universe might be metastable, not perfectly stable, but stable enough to last billions of years. Probably, it's like living in a wooden house that stood for centuries, unaware that termites have been gnawing at its foundation. The unsettling truth is that the Higgs field's current state appears finely balanced. If it were even slightly different, the universe would either have collapsed instantly after the Big Bang or lack the structure to form galaxies. That perfect calibration hints at either astonishing cosmic luck or deeper laws we've yet to uncover. Where does this leave us for now, safely in the probably stable camp? Calculations suggest any spontaneous Higgs transition would take longer than the current age of the universe to occur. But the uncertainty has spurred wild ideas, from theories about hidden particles that stabilize the field to speculation that black holes might catalyze the process. Some researchers even propose that we could detect early warning signs of vacuum decay through subtle changes in fundamental constants or unexpected particle behavior in colliders. The irony is poetic. The same field, THAT Chinese letter, Chinese letter, Chinese letter, Chinese letter, Chinese letter, Chinese letter, that makes existence tangible, might also contain the seeds of its own undoing, yet this fragility could be a clue to something grander. Perhaps the Higgs field's precarious state points to undiscovered physics, extra dimensions, parallel universes, or forces that balance quantum fluctuations in ways we can't yet see. Every measurement of the Higgs boson, every collision in particle accelerators, brings us closer to understanding whether our cosmic home is built on bedrock or a house of cards waiting for the right quantum breeze. At the heart of the Higgs field's power lies a deceptively simple number, 246 gigaelectronvolts. This isn't just a random value, it's the vacuum expectation value, or VEV, the Higgs field's baseline energy level that permeates every cubic centimeter of the universe. Think of it as the universal default setting, an invisible undercurrent shaping reality itself. The moment this field settled into its current VV shortly after the Big Bang, it didn't just nudge particles toward having mass, it determined exactly how much mass each one would carry. The VV operates like a cosmic measuring stick. When particles interact with the Higgs field, their mass isn't arbitrary. It's directly proportional to how strongly they couple to this universal baseline. An electron barely taps into the field's energy, like someone dipping a toe into a pool, which is why it's so lightweight. A top quark, by contrast, plunges in fully, soaking up the field's influence and emerging hundreds of thousands of times heavier. Even the Higgs boson itself derives its mass from the VV, like a ripple measuring the depth of the water it moves through. What's fascinating is how this single number orchestrates such staggering variety. The VV acts like a master dial, tuning everything from the mass of the tiniest neutrino to the stability of galaxies. If this value were slightly higher, atoms might have been too bulky to form complex molecules. Slightly lower, and stars could have burned out before life had a chance to emerge. It's a precision calibration that borders on the uncanny one that begs the question, why this particular value and not another? Some theorists argue it's evidence of a multiverse, where countless universes flicker into existence with different VVs, and we just happen to inhabit one where the number permits our existence. Others suspect deeper physics at play, perhaps undiscovered symmetries or particles that anchor the field to this exact energy. Experiments at the Large Hadron Collider are now scrutinizing the Higgs boson's properties to reverse engineer the VV's origins. By measuring how the boson interacts with other particles, and itself, scientists hope to uncover whether this critical number is fixed by necessity or cosmic accident. The answers could redefine our understanding of everything from quantum fluctuations to the universe's ultimate fate. Because the VV isn't just a static number, it's the silent architect of mass, the invisible hand that shaped the universe into a place where matter and life could take hold. The discovery of the Higgs field didn't just complete the standard model, it ripped open its seams, revealing tantalizing gaps that point toward something far grander. For all its brilliance, the standard model is like a flawless map that only covers half the territory. It doesn't account for gravity. It leaves dark matter as a haunting blank space. And most puzzling of all, it can't explain why the Higgs boson is so inexplicably light. These aren't just loose ends, they're cosmic breadcrumbs leading us toward physics beyond anything we've ever imagined. Take string theory, for instance, the idea that all particles are actually tiny, vibrating strings in a universe with 10 or 11 dimensions. At first glance, it seems like pure mathematics untethered from reality. But the Higgs field might be the bridge connecting these abstract concepts to the tangible world. String theory predicts not just one Higgs field, but a whole family of them, each potentially shaping different aspects of reality in higher dimensional space. Some theorists suggest that what we perceive as the Higgs boson could be just the three-dimensional shadow of these richer, multidimensional fields, like hearing a single note from an orchestra playing in another room. Then there's the enigma of extra dimensions. If they exist curled up smaller than an atom, the Higgs field might be our best tool for detecting them. Picture this: the field's value, that critical 246 gigaelectronvolts, could be influenced by hidden dimensions tugging on it from beyond our perception. Experiments at the Large Hadron Collider are already hunting for anomalies in how the Higgs boson decays, hoping to catch glimpses of these invisible realms. A slight deviation from predictions might reveal particles momentarily slipping into higher dimensions before snapping back into our observable universe. But perhaps the most electrifying possibility is that the Higgs field isn't alone. Just as light coexists with radio waves and X-rays in the electromagnetic spectrum, there might be entire sectors of dark Higgs fields interacting only with dark matter. This could explain why 85% of the universe's mass remains invisible to us. If true, it would mean we've been studying just one instrument in a vast cosmic symphony, oblivious to the other players. What's striking is how these wild ideas aren't pure speculation. They're forced upon us by the Higgs field's quirks. Its bizarrely low mass, its potential instability, even the way it might connect to gravity. All these anomalies whisper that our current model is merely the first chapter in a much longer story. The Higgs boson isn't the final answer, it's the flashlight illuminating the path forward. And as we follow that light into uncharted territory, we might discover that the true nature of reality is stranger, richer, and more interconnected than we ever dared to dream. From blockbuster films to best-selling novels, the Higgs field has leaped from physics journals into the spotlight of pop culture, often with more dramatic flair than scientific accuracy. Take Marvel's Ant-Man movies, where shrinking particles bypass the laws of physics with a handwave about quantum realms and mass manipulation. While real-world Higgs mechanics don't let heroes ride ants like scooters, the films tap into a genuine curiosity. What if we could tweak mass at will? The irony is delicious. Hollywood's fantastical versions sometimes spark more public interest in the real science than textbooks ever could. Then there's the Big Bang Theory, where Sheldon Cooper's obsession with the Higgs boson turned phrases like God particle into living room chatter. The show's mix of humor and half-truths, like Leonard joking about Higgs bosons showing up at parties uninvited, played fast and loose with the facts but made particle physics feel relatable. It's a reminder that pop culture doesn't need perfect precision to make science thrilling. Sometimes all it takes is a well-timed laugh to get people asking, wait, is that really a thing? Literature takes even bolder liberties. Dan Brown's Angels and Demons wove Higgs research into a thriller about antimatter bombs, blending CERN real tunnels with fictional doomsday tech. Meanwhile, the Three-Body Problem trilogy imagines aliens weaponizing quantum physics, bending fields like the Higgs into tools for interstellar sabotage. These stories stretch reality like taffy, but they share a kernel of truth. The Higgs field does underpin the stability of matter, and tampering with it could theoretically unravel reality itself. Even video games get in on the action. Destiny 2 features a weapon called Higgs Boson Adept, firing black hole bullets that defy physics. It's pure fantasy, but the game's lore nods to real science, framing the Higgs as a cosmic force players harness like magic. And in Mass Effect, the fictional Mass Effect fields used for FTL travel, they're basically Higgs fields on steroids, tweaking mass to propel ships faster than light. What's fascinating is how these portrayals reflect society's hopes and fears about cutting-edge science. the Higgs becomes a metaphor for humanity's ambition to control nature's fundamental forces for better or worse. Some depictions lean into doomsday scenarios looking at you, 2012 pseudoscience, while others, like Contact, use it as a springboard for existential wonder. The common thread, whether as a plot device or punchline, the Higgs field has cemented itself in our collective imagination, not as equations on a chalkboard, but as a gateway to the universe's greatest mysteries. Perhaps the most telling impact lies outside fiction. When the Higgs boson was discovered, late-night hosts cracked jokes, news anchors stumbled over gigaelectron volts, and The Simpsons aired a couch gag with Homer accidentally finding the particle. That cultural saturation is its own kind of breakthrough proof that even the most abstract physics can become shared folklore. So while physicists might cringe at Hollywood's creative licenses, they'll also admit, if a superhero movie gets someone curious enough to Google Higgs Mechanism, that's a win science didn't see coming. One of the biggest myths about the Higgs field is that it drags on particles like molasses slowing down a spoon, as if mass were just cosmic friction. In reality, the interaction is far more subtle. Particles don't get bogged down by the field. Instead, their mass emerges from how deeply they couple with it. Think of it like tuning a radio. Photons skip past the dial entirely, while quarks land on a frequency that resonates intensely with the Higgs field. That resonance isn't resistance, it's more like a particle finding its unique harmony with the universe's underlying structure. The heavier the particle, the richer that harmony becomes. Then there's the infamous God particle nickname, coined not by scientists but by a publisher trying to sell books. The term suggests the Higgs boson is some divine keystone holding reality together, when in truth, it's just a ripple in the field, one piece of a much larger puzzle. Nobel laureate Leon Lederman originally titled his book The Goddamn Particle out of frustration with how hard it was to detect, but editors scrubbed the profanity, accidentally creating a myth that overshadows the real science. Calling it divine also implies purpose when physics reveals only mechanism. The Higgs field doesn't choose which particles gain mass. Their interactions are dictated by cold, elegant mathematics. Another misconception that the Higgs field fills space like an invisible liquid. While it's everywhere, it doesn't displace anything or push particles around. Empty space isn't truly empty, it's humming with quantum activity. But the Higgs field is less a substance and more a condition of the universe, like the rules of geometry shaping how objects move. Imagine sitting in a room where the air governs how fast you can walk. The air isn't grabbing your legs, it's the medium that defines the interaction. Perhaps the most persistent error is conflating the Higgs field with gravity. While both involve mass, gravity curves spacetime itself, while the Higgs field merely gives particles their intrinsic mass. A bowling ball bends a trampoline gravity, but the ball's weight comes from its Higgs interactions. This distinction matters because it means someday we might manipulate mass without touching gravity, or vice versa. These misunderstandings aren't just academic nitpicks, they shape how we imagine future technologies, from anti-gravity devices to energy breakthroughs. The Higgs field isn't magic, it's machinery, and like any finely tuned machine, the real wonder lies not in mystifying it, but in understanding exactly how its gears turn. The next decade of particle physics promises to peel back even deeper layers of the Higgs field's mysteries, with upgrades to the Large Hadron Collider and next-generation experiments poised to rewrite the rules. In 2029, the high-luminosity LHC will begin slamming protons together at unprecedented rates, generating 15 million Higgs bosons per year, 10 times today's tally. This deluge of data could reveal the boson's rarest decay pathways, like whispers of interactions with hypothesized dark matter particles or hidden dimensions. Picture combing through a haystack not just for needles, but for threads of silk invisible to current sensors, each one a potential clue to physics beyond the standard model. Meanwhile, Japan's planned International Linear Collider offers a surgical alternative to the LHC's brute force approach. Instead of circular collisions, it would fire electrons and positrons in straight-line beams, producing Higgs bosons in ultra-clean environments free from proton collision debris. Think of it as swapping a sledgehammer for a scalpel precision that could measure the Higgs properties with error margins finer than 1%. Such exactness might uncover subtle anomalies like slight deviations in how the boson couples to muons versus electrons, hinting at undiscovered forces or particles. But the boldest frontier lies in proposals like the Future Circular Collider, a 91-kilometer ring beneath the Alps that could reach energies 7 times the LHC's peak. Here, scientists might produce Higgs bosons in pairs, probing how the field interacts with itself. This self-coupling is the universe's ultimate feedback loop, determining whether the Higgs field's vacuum state is truly stable or a precarious illusion. The answers could redefine our cosmic expiration date. Beyond colliders, tabletop experiments are hunting for Higgs field shadows in unexpected places. Quantum sensors now scan for infinitesimal variations in electron behavior that might betray the field's influence at low energies. Others analyze neutron stars where extreme gravity might warp the Higgs field in detectable ways. Even atomic clocks so precise they'd lose less than a second over the age of the universe are being repurposed to spot fluctuations in fundamental constants tied to the field's behavior. The common thread: each experiment approaches the Higgs enigma from a different angle, like detectives reconstructing a crime scene from fingerprints, security footage, and witness accounts. What emerges won't just fill textbooks, it could expose whether the Higgs is the universe's final answer or just the first clue in a far grander mystery. One thing's certain: the era of Higgs physics has only just begun. The Higgs field isn't just a quirky detail of particle physics, it's woven into the fate of the cosmos itself, with implications stretching from the universe's first moments to its possible demise. Rewind to the Big Bang, and you'd find a scene of unimaginable energy where the Higgs field was trapped in a high-energy state, like a marble balanced on the crest of a hill. This wasn't just a quirk of the early universe, it might have been the engine behind inflation, the explosive expansion that stretched space from subatomic to cosmic scales in a fraction of a second. Some theories suggest the Higgs field, or something like it, could have been the inflation, the hypothetical force that drove this rapid stretching. Picture a snow globe shaken violently. The sudden release of energy sends flakes flying outward, much like how inflation propelled galaxies apart. If the Higgs played this role, it didn't just give particles mass, it sculpted the vast, structured universe we see today. But the field's influence doesn't stop there. Modern measurements suggest the Higgs field exists in a precarious state, a false vacuum that's stable for now, but not necessarily forever. Think of it like a ball resting in a shallow valley with a deeper valley just beyond the next hill. Quantum fluctuations could, in theory, nudge the field over that hill, triggering a catastrophic phase transition. If this vacuum decay ever occurred, it wouldn't just tweak the laws of physics, it would rewrite them. A bubble of true vacuum would expand at the speed of light, annihilating atoms, stars, and space-time itself as it advanced. The unsettling part: we wouldn't see it coming. One moment, reality would function as usual. The next, everything would cease to exist in a wave of fundamental transformation. This isn't just doom-mongering, it's a mathematical possibility embedded in the Higgs field's properties. The fact that we exist to ponder it, though, suggests the universe is sitting in a metastable sweet spot where the field's current state has held firm for billions of years. But subtle clues hint at how close we might be to the edge. The Higgs boson's mass, measured at 125 gigaelectronvolts, is light enough to suggest the field is in a false vacuum, but heavy enough to buy us time. Some calculations estimate the universe could persist for tens of billions of years before a random quantum fluctuation sparks decay. Others speculate that high-energy events, like black hole collisions or particle collisions at future colliders, might nudge the field prematurely. Yet even this apocalyptic scenario carries a silver lining. If the Higgs field's instability is real, it might point to deeper physics waiting to be discovered. Just as the Boson's discovery validated decades of theory, vacuum decay predictions could hint at missing pieces, new particles, extra dimensions, or symmetries that stabilize the field. Some models propose a supersymmetric Higgs where undiscovered particles act as cosmic scaffolding, anchoring the field firmly in its current state. Others imagine a multiverse where each universe has its own Higgs configuration, and we just happen to live in one where the numbers permit galaxies and life to exist. What's striking is how these cosmic stakes trace back to a single field's behavior. The same mechanism that gives mass to electrons and quarks also holds the universe's future in balance. Whether through colossal colliders, space-based telescopes, or tabletop quantum experiments, scientists are racing to measure the Higgs field's properties with ever greater precision, not just to satisfy curiosity, but to glimpse whether reality is built on bedrock or a house of cards. The answers won't just reshape physics, they'll redefine our place in a cosmos where even the most fundamental forces are still writing their own rules. The Higgs field does more than dictate the mass of particles. It forces us to confront profound philosophical questions about the very nature of reality. Consider this: every atom in your body, every star in the sky, owes its tangible existence to an invisible, intangible field that permeates the cosmos. What does it mean for our understanding of realness when the foundation of matter itself is woven from something we can neither see nor touch? It's as if the universe operates like an intricate simulation, with the Higgs field serving as its underlying code, a hidden framework that determines how objects manifest within the rules of our existence. This challenges the classical divide between the concrete and the abstract, blurring the line between what we perceive as solid and the ethereal forces that make that solidity possible. Delve deeper, and the Higgs field raises existential questions about fine-tuning and purpose. The field's exact energy value, 246 gigaelectronvolts, isn't arbitrary. It's a number so precisely calibrated that even a slight deviation would render atoms unstable, preventing galaxies, planets, or life from ever forming. Does this precision suggest a universe designed with intention, or is it merely a statistical fluke in an infinite multiverse where countless other configurations fail to sustain complexity? The Higgs field doesn't just give particles mass, it amplifies the age-old debate between determinism and chance, leaving us to wonder whether our reality is the product of meticulous engineering or cosmic luck. Then there's the humbling realization of scale. The Higgs field is omnipresent, yet its effects are felt most profoundly in the quantum realm, a domain so small it defies everyday intuition. This duality mirrors humanity's place in the cosmos. We are inconceivably tiny compared to the universe's vastness, yet we've developed the intellect to decode its deepest secrets. There's poetry in the idea that the same field granting mass to quarks also binds the neurons in a scientist's brain as they ponder its meaning, a cosmic loop of curiosity and discovery. But perhaps the most unsettling implication is the Higgs field's potential impermanence. If the universe's vacuum state is metastable, as some measurements suggest, then the laws of physics as we know them might be temporary, a fleeting configuration in an eternally shifting landscape. This unsettling possibility reframes human achievement and ambition. Everything we've built, every thought we've had, exists within a framework that could, in theory, vanish in an instant. Yet rather than diminish our significance, this fragility underscores the remarkable improbability of our moment in cosmic history. We are here, against staggering odds, to witness and interrogate the very forces that make our existence possible. The Higgs field ultimately invites us to reconsider not just how the universe works, but why we're here to ask the question at all. It's a reminder that science doesn't strip the world of wonder, it deepens it, revealing layers of mystery that stretch far beyond the tangible. Whether through the lens of philosophy, theology, or sheer curiosity, the Higgs field doesn't just explain mass. It compels us to grapple with what it means to exist in a universe governed by invisible, enigmatic rules, and what truths might still lie hidden in the quantum shadows. Bringing the mind-bending concepts of the Higgs field down to Earth has become a mission for science communicators worldwide, and they're getting creative. Take YouTube's Veritasium, which used a simple pool filled with plastic balls to visualize how particles gain mass. As presenters waded through the sea of spheres, viewers could instantly grasp how resistance mimics the Higgs mechanism. No advanced degree required. Over on Minute Physics, whiteboard animations transform abstract quantum field theory into bite-sized, colorful sketches where particles become characters in a cosmic story. These channels prove complex ideas don't need dilution, just clever translation. Museums have taken immersion to the next level. London's Science Museum features a gleaming, interactive Higgs field exhibit where visitors tune virtual particles, watching their masses change in real time as they adjust coupling strengths. In Chicago, the Museum of Science and Industry built a walk-through quantum tunnel where light projections simulate the Higgs field's omnipresence, surrounding guests in shimmering equations that respond to their movements. Even CERN itself offers virtual reality experiences, letting anyone don a headset to ride alongside protons during LHC collisions, an adrenaline-pumping way to demystify particle acceleration. The most unexpected outreach might be the Higgs-in-a-Box kits distributed to schools worldwide. Developed by CERN physicists, these contain simple analogies, like magnets of different strength representing particles with varying Higgs interactions. Students physically feel the pull resistance, internalizing concepts textbooks take chapters to explain. Some kits even include augmented reality apps that animate Higgs boson decays when viewed through a phone, blending tactile and digital learning. For those craving deeper dives, platforms like Brilliant and Coursera offer interactive courses where learners adjust Higgs field parameters in simulations, witnessing firsthand how tweaking the vacuum expectation value would alter atomic stability. These tools don't shy away from math but present it through sliders and visual outputs rather than dense equations. Even social media has joined the effort. TikTok creators use domino chains and synchronized dancers to model symmetry breaking, proving particle physics can trend alongside viral challenges. The common thread, meeting people where they are. A high school student might grasp the Higgs mechanism through VR gaming, while a retiree connects with podcast narratives comparing the field to an invisible orchestra tuning the universe. By embracing multiple entry points, hands-on, visual, narrative, these initiatives reveal a truth often lost in academia. Understanding doesn't require memorizing Feynman diagrams. Sometimes it just takes the right metaphor, the perfect demonstration, or that one aha moment when the cosmos clicks into place. Perhaps the most profound impact lies beyond facts. It's the cultural shift making quantum physics dinner table conversation. When children sketch Higgs bosons alongside dinosaurs and astronauts, when musicians compose symphonies inspired by vacuum fluctuations, science ceases to be a remote priesthood. The Higgs field becomes what it truly is, not just a particle physicist's specialty, but a shared story about how reality works, waiting for anyone curious enough to listen. When the Higgs boson discovery made headlines in 2012, it wasn't just physicists celebrating classrooms lit up with wide-eyed fascination. Take 14-year-old Mia, who stumbled upon the news while scrolling science blogs on her phone. The idea that an invisible field gave her pencil, her desk, even her own body their weight captivated her in a way textbooks never had. She spent weeks building a cloud chamber from an old fish tank to track cosmic rays, chasing her own glimpse of particle magic. Today, she's completing her PhD. In quantum field theory, part of a wave of researchers who trace their passion back to that monumental summer. Stories like Mia's aren't rare. At CERN annual beamline for schools competition, teenagers from Nairobi to Oslo design particle physics experiments with the same fervor as pop song covers. One group even proposed using antimatter to test if the Higgs field interacts differently with matter's mirror image, an idea so clever it earned them beam time alongside seasoned physicists. This is the Higgs discovery's unsung legacy, not just filling gaps in equations, but igniting imaginations that will shape science for decades. What makes the Higgs uniquely inspiring is its democratic wonder. You don't need a lab to ponder its mysteries. 12-year-old Jamal replicated the symmetry-breaking concept with dominoes in his Brooklyn apartment, filming the moment a tiny nudge made them cascade into unexpected patterns. His video went viral, landing him a mentorship with a Fermilab researcher who recognized the same intuitive spark Peter Higgs once had. In rural India, sisters Priya and Ananya used smartphone sensors to measure muons from cosmic rays particles whose mass comes from that very field. Their makeshift detector, built from recycled electronics, won them scholarships to study particle physics. This global ripple effect underscores a profound truth. Curiosity thrives when science feels expansive, not exclusive. The Higgs boson became a gateway because it embodied riddles anyone could grasp: why things have weight, how emptiness shapes reality, while hinting at deeper layers awaiting exploration. Universities now report surging enrollments in particle physics courses, with applicants citing documentaries like Particle Fever that captured the human drama behind the data. Yet the real lesson isn't just about recruitment. When young researchers ask why pursue questions with no obvious application, the Higgs offers the perfect rebuttal. Its discovery required decades of blind faith in pure research. No one in 1964 could have predicted its role in modern medical imaging or materials science. The students launching neutrino experiments in garage workshops today might be laying groundwork for technologies we can't yet name. That's why leading physicists now spend as much time in elementary schools as collider control rooms. They know the next breakthrough might come from a child staring at soap bubbles, wondering if their shimmering surfaces hold secrets about quantum fields. By framing the Higgs not as an endpoint but an invitation, science keeps its most vital promise, that the universe always has more wonders to reveal, and every generation deserves the thrill of uncovering them. From the moment Peter Higgs scribbled his revolutionary equations to the triumphant detection of the boson that bears his name, the journey to unravel the universe's hidden architecture has reshaped our understanding of reality itself. The Higgs field isn't just another entry in physics textbooks, it's the invisible choreographer of existence, dictating why particles have mass, why atoms stick together, and why the cosmos didn't remain a formless void after the Big Bang. Its discovery didn't just fill a gap in the standard model, it revealed a cosmos where emptiness hums with latent energy, where what we call nothing is in fact a dynamic stage for creation. Think of how far we've come, from ancient philosophers speculating about earth and fire, to colliders so precise they can recreate conditions last seen a trillionth of a second after the universe began. The Higgs boson's detection was a triumph of human ingenuity, a decades-long quest involving thousands of scientists, mountains of data, and a machine colder than interstellar space. Yet for all its complexity, the takeaway is elegantly simple. Mass isn't an inherent property. It's a conversation between particles and this omnipresent field, a dialogue that shapes everything from the electrons in your devices to the distant glow of collapsing stars. But the implications stretch far beyond theory. The technologies born from this pursuit, superconducting magnets, advanced computing grids, even the internet itself, have transformed medicine, energy, and communication in ways Higgs himself never imagined. Who could have predicted that hunting an elusive quantum ripple would lead to life-saving cancer therapies or the backbone of global connectivity? This is the beautiful paradox of fundamental research. The questions seem abstract, but their answers often rewrite daily life. Yet the most exhilarating chapter may still lie ahead. The Higgs field's quirks, its puzzling lightness, its precarious stability, hint at deeper layers of reality waiting to be uncovered. Could supersymmetry lurk just beyond our current energy scales? Are there dark siblings of the Higgs field governing unseen matter? Every new experiment, every upgraded collider brings us closer to these revelations. The field isn't just a solved puzzle, it's a Rosetta Stone for questions we're only beginning to articulate. So as we stand on the threshold of the unknown, let's not forget the lesson woven into this discovery. Curiosity is humanity's superpower. Whether you're a student sketching particle interactions in a notebook, a coder refining algorithms to sift cosmic data, or simply someone who gazes at the night sky in wonder, you're part of this grand investigation. The universe doesn't give up its secrets easily, but as the Higgs field reminds us, even the most invisible forces leave fingerprints. Stay alert to them. Stay hungry for the next mystery, because somewhere, perhaps in a lab or a classroom or a daydream, the next great revelation is already taking shape. And who knows, the hand that uncovers it might be yours. If this dive into the Higgs field left your brain buzzing with questions, you're not alone. This is the kind of science that keeps us up at night too. Before you go, hit that like button if you enjoyed unraveling the universe's secrets with us, and subscribe to stay plugged into more mind-bending explorations. Every click helps us chase down the next big mystery, from quantum quirks to cosmic collisions. Now, we want to hear your theories. Drop a comment below telling us which Higgs revelation blew your mind the most. Was it the idea that mass is just a cosmic handshake between particles and an invisible field? Or maybe the wild possibility that our universe is balanced on a quantum knife edge? Your thoughts fuel this community, and we read every single one. For those hungry to go deeper, we've curated a playlist called Beyond the Standard Model, link below, that tackles everything from supersymmetry to string theory. And if you're craving hands-on learning, check out CERN virtual tours or the Higgs Field simulator app. Yes, that's a real thing where you can tweak particle masses yourself. One last thing, share this with someone who loves a good what if. Maybe it's your physics-obsessed niece, your debate-loving roommate, or that coworker who always asks why the universe works the way it does. Science is a team sport, and every new perspective brings us closer to cracking these cosmic codes. Thanks for geeking out with us. We'll see you in the next episode, where we're venturing into the quantum shadows to hunt for dark matter. Until then, keep looking up and questioning everything.